All right. I want to talk real quick about kind of the big take-home ideas from today's free fall lab that it was a little hard to get at during class today. So, the first question on the analysis questions is how does mass affect the acceleration of an object in free fall? And we went outside and I showed you that no matter what the mass was, whether it was a crumpled up piece of paper or, like, say, a bowling ball, they're both going to fall to the ground at the same acceleration. Gravity's acceleration is the same no matter what the mass. Now, we did see, however, outside that if it was like a flat piece of paper, that paper kind of slowly made its way down, and that's because of air resistance. So if you remove air resistance, then objects will accelerate due to gravity at the exact same rate. Now, what is that rate? What is the acceleration due to gravity? The acceleration due to gravity is negative 9.8 meters per second squared. Now, that's what you should have gotten on your graphs. So the slope of your velocity time graphs should have been negative 9.8. Some of them were close, some of them were further off. It all kind of depended on how accurate you were. Like, I'm looking right now, and one group got negative 10, another group got negative 7, another group got negative 11.8, negative 7.8, negative 8.2. So ultimately, like, we spent a lot of time crunching the data, and we got pretty good results. If I were to average those values, it would all average to right around negative 9.8. To answer the next question here, which is, for a ball that's tossed straight up, how does the acceleration on the way up compare to the acceleration on the way down? I'm just going to assume that the acceleration due to gravity is actually negative 10 meters per second squared, just to keep the numbers a little simpler. And the answer to the question, I'll tell you right now, spoiler, is that it stays the same on the way up and on the way down. And here's why. The negative sign just means that acceleration points downwards. That's all the negative sign means there. And so for example, and then acceleration means your change in velocity. So for example, if we were to throw a ball straight up with a velocity of, let's say, like 40 meters per second, because of the acceleration of gravity, and let's say that it's negative 10, what's going to happen is 1 second later, negative 10 meters per second squared, 1 second later, that ball is going to be moving slower. In fact, 1 second later, the ball is only going to be going 30 meters per second. Okay, and then you can kind of see where this is going. And then a second after that, it's going to be, because of gravity's going to slow it down. It's only going to be going 20 meters per second. And then a second after that, gravity's going to slow it down more to 10 meters per second. And finally, when it reaches the apex, gravity will have slowed it down to 0 meters per second. So if you throw a ball up at 40 meters per second, then about 4 seconds later, the object's going to reach its apex. And that's because gravity is pointing downwards with a gravitational acceleration of negative 10 meters per second the whole time. So what happens then? Well, the ball doesn't just stay there. Gravity continues to accelerate it downwards at a rate of negative 10 meters per second squared. So how is the velocity going to change from 0? It's going to change by a value of negative 10. So it's going to now, on the way down, it's going to be going 1 second later, negative 10 with a speed of negative 10 meters per second, or velocity. And then a second after that, negative 20 meters per second. And a second after that, negative 30 meters per second. And finally, once it reaches the same height it was launched from, it's going to be going at negative 40 meters per second. And so there's some nice, what we like to call symmetry. And that symmetry arises because gravity is negative 10 meters per second squared. The acceleration of gravity is negative 10 meters per second squared the entire time, and it points down. How does that answer our question? Well, the question was, how does the acceleration on the way up compare to the acceleration on the way down? And the answer is that it's constant. Sometimes people will make the mistake of saying, acceleration points up on the way up and down on the way down. But imagine that for a moment with me, that gravity's acceleration did point up on the way up. Well, then that 10 meters per second squared would be positive, and it would make the 40 meters per second that we throw it up with it would make it increase. So in 1 second, it would, instead of being going 40, it would go 50, and then it would go 60, and then 70. So it would never reach an apex. It would just go faster and faster and faster as the object rises. But that's not how gravity works. Gravity points down the whole time, which means that it slows the object down on the way up, and then it speeds the object up on the way down. At the maximum height, the apex, well, we've already kind of addressed that. The last two questions in our analysis have to do with discussing the velocity and the acceleration at the apex. And so at the apex, we've already talked about it, really, but you may not have realized it. At the apex, the velocity is 0. That's the moment it stops. So when you throw an object up, it stops for a moment when it reaches the apex. But if acceleration were 0, and a lot of people make the mistake of saying, oh, at the apex, the velocity is 0, and they say the acceleration is 0 meters per second squared. Well, if the acceleration were, in fact, 0 meters per second squared at the apex, then there would be no change in velocity, right? Because acceleration is the change in velocity. And if there's no change in velocity, well, then the ball's velocity or object's velocity would remain at 0 meters per second, which means it would stay at rest. So there would be this weird thing in the world where if you threw something up to the apex, it would reach the apex, stop, and stay stopped if the acceleration were, in fact, 0 at the apex. But it is not, right? Acceleration at the apex is still negative 9.8, or we can round that to negative 10 meters per second squared. And that explains why when the object reaches the apex and it reaches a velocity of 0, that velocity is still going to change and it's going to start moving downwards. All right, that's a nice little summary of the freefall lab, which I tried to explain to you today at the end of the class, but it was kind of rushed and you may not have gotten all those details. Hopefully it makes sense to you. Have a great rest of your day. I'll see you later. Bye-bye.